So good evening, everybody. So it's just about time to start. We are at 6:30 p.m. IST over here. So good evening for people who are joining us from India. For those, I think there are many people who are joining us from UK and some others from other regions as well. So welcome you all to this chat about sustainable concrete solutions. We'll hear more from the expert, Dr. Sean Monkman. But before we get to that, I would quickly run through a brief introduction about IC itself, what we are trying to do, and also touch upon what we are trying to do within the Mumbai region itself. I am Rajesh Patwardhan. I am the IC representative for Mumbai region. We'll quickly touch upon various things that we are actually trying to do. Briefly about IC, we actually are a not-for-profit organization working across the the entire civil engineering fraternity itself. So that's sort of the kind of coverage that we as an organization actually are able to include, which is the whole world of civil engineering is huge. I think there are multiple different infrastructure angles that actually come into play. Infrastructure which is so critical for human life, and I think I'm pretty proud that we are all members of IC over here. I think some of you are, some of you aren't, and I would more than welcome those who are online and want to be a part of IC. Feel free to contact me, and I'll be able to help you become a member of IC and be a proud member of IC, continuing the reputation that IC actually has built. It's a 90,000 plus members across the globe, across 162 countries. We are internationally very well respected organization, essentially a body of a qualifying body for civil engineers. When I say qualifying, it's essentially affiliated to the Engineering Council of UK. So they are able to award the chartered engineer title based on the requirements of the ECUK once you have fulfilled a certain set of attributes. I'm not going to touch upon too many details about that on this particular call, but again, feel free to contact me in case you need some more information about this. IC again has got a whole plethora of knowledge, being a 200-year-old organization, 200-year-plus-year-old organization. Uh, the knowledge that the institution actually carries is really fantastic, and all of this is actually accessible to our members. Benefits of membership apart from the knowledge sharing, we are actually talking about we are a part of this event that we are hosting from Mumbai right now. Again, pretty happy to say that Mumbai Association has been pretty active in conducting some very interesting discussions, got some experts from different fields to talk about various subjects of interest, essentially focused around civil infrastructure. We have actually tried to get a very interesting set of discussions through Genesis Tech Talk series, which is the monthly Tech Talk series that we conduct. We have been conducting for the last more than 3 years now. Uh, Apart from that, IC supports continual professional development. Again, professional development is very important. I think globally there's a lot of recognition to keep knowledge abreast of what's actually happening across the globe. And as the globe becomes globally, as I think engineers become more and more integrated, we need to work as teams. I think continual professional development becomes all the more important. And that's where IC actually provides a lot of support. So there is a host of other things that IC does, including IC rewards, benevolent fund, and I think if anybody's interested to understand what all of these benefits actually are, feel free to connect with me, and I'll try to help to the extent possible. Uh, as far as IC memberships are concerned, these are the 5 grades of membership that you see, starting from graduate member, or rather, starting from student member to a fellow. And fellow is obviously the highest grade of membership of the IC. If anybody is interested to understand the CPD professional, how to acquire professional qualifications, these are all available through webinars. You will see a link available on top of this particular slide. And again, if anybody is interested to have access to this, feel free to connect with me, and I'll be more than happy to share with you. Patrick Courtney is our international membership recruitment manager based out of UK. and that's his email address. If you want to if you are interested to understand more about international membership, how IC is connected globally, and so on and so forth, feel free to connect to Patrick, and you can copy me in as well. If you're based out of India, I'll be able to leverage whatever support is available from India itself. Talking about Mumbai region, I am the regional representative. As I mentioned, those are my coordinates. I am one of the 3 approved mentors of IC, and I can help professionals to go through their career development and become a chartered as well. So again, anybody interested, more than happy to support and connect with you as well. Feel free to contact me via email or otherwise through mobile phone as well, and I'll be more than happy to support. The Mumbai Association itself, that's sort of the numbers, the key numbers of the region itself. We have 200 plus members connected across the state of Maharashtra, Goa, and Gujarat. And we have got a number of members, fellow members, as well as technicians and graduate members across the entire region. Being relevant is pretty important to a not-for-profit organization like ICE, and we try to do that through various relevant events that we conduct. From time to time, Genesis was launched about 3 years back, and this is the 21st edition of Genesis. Apart from that, we have been conducting various interesting site visits. The pictures that you see, for example, the one that you see on the left-hand side and the center, there was a site visit to world's tallest statue, which was recently completed in India. And I think about 15 professionals actually had the chance to go right up there and witness the fantastic engineering construction job that has been accomplished over here. It was a marvelous feat that has been accomplished, really worthwhile seeing. In addition to all of what I've shared right now, recently in December, IC has launched what is referred to as the Enabling Better Infrastructure Program. And I have got a short video which talks about this particular stuff. So let's hear Dr. Michael speak about it.
Across the globe, there are some common issues being faced by decision makers. The need to address climate change and its effect, the need to manage rapid urbanization and demographic shifts, and the need to enable the opportunities brought by digitization and new technology to boost economies. Now, these changes will lead to increasing requirements for new and repurposed infrastructure. Getting this right is the responsibility of national governments. So where should they start? How do they plan and prioritize national infrastructure? The very nature of these challenges means that for many governments, this will be the first time they've had to address these issues in a strategic way. So what does our program do, the Enabling Better Infrastructure Program? Rather than see government decision makers around the world reinventing the wheel, the Enabling Better Infrastructure Program partners have created an online resource hub that shows the different approaches that have been taken to infrastructure planning and delivery. No one country has the monopoly on good ideas. So bringing together examples and learnings from around the world, we hope to increase the likelihood of decision makers getting it right first time. Ensuring societies get the infrastructure systems they need and can trust, and to be ensured that they are delivered in the right way, for the right budget and the right time. Now, that is the objective of the Enabling Better Infrastructure Program.
Right. So as he mentioned, in fact, in his video, you can see on the screen the resource hub that's actually created by IC. It contains some very fantastic literature about infrastructure planning. What are the important elements? What is the framework that's actually available, which can actually enable better infrastructure planning going forward, especially that meets the current prerequisites in terms of issues related to dealing with climate change which is again becoming an integral part of various infrastructure offerings. And I think that's becoming a bigger and bigger focus going forward. And I'm quite glad that IC is actually already building such tools and frameworks which can actually help planners, designers take cues from and build a better infrastructure globally. So, so that's talking about the enabling better infrastructure. With that, I conclude my very brief chat. I will stop sharing my screen now. I request Dr. Sean Monkman to commence with his introduction and his presentation. In the meantime, I would request all who are attending this session to kindly type in their names and their location in the chat box so that we know who you are. I think some of the email addresses that I see, they don't carry names, so we are not able to understand who is joined in. So feel free to add to the chat box your names and your location, please. Thank you very much, and over to Dr. Sean.
Thank you, Rajesh. I'm pleased to be here, and thank you for everyone who has signed up for this this talk. If I'm not mistaken, my talk is now on the screen.
Yeah, it is. Dr. Sean, would you like to enable your video so that people can see you live, if you're okay with it?
Yeah, I just have to find the window now.
Sure.
Gosh. Oh, okay, there it is. There. Okay. As far as I know, we're ready to go. So thank you, everyone who has expressed interest in joining this talk, and thank you for the ICE for...
Sean, actually, your screen is looking split right now, so can you just maximize it? Probably there's some issue with what we are able to see right now.
What do you mean split?
It's split into two separate parts. I'm seeing two portions. One is the current slide and one is the next slide. So probably you just need to maximize the screen, probably.
How's that?
Yeah, that's correct. Yeah, that's good. Thanks.
Okay, sorry. That didn't happen the other day. Okay, so thank you for extending the opportunity and allowing myself to talk about what we're doing with a technology company in Canada called CarbonCure Technologies, and how that ties into the civil engineering environment and how the goals for the greater industry to be more sustainable. So I'll describe what we're doing and the impacts we're making and what that means. Just as an outline of the topics I will cover, I'm assuming most people have not heard of CarbonCure, so I'll give you a little bit of background about who we are. I'll go a bit broader and talk about concrete and why it's used, and then our role in what we're doing for the concrete industry. I'll describe the value proposition about what we're offering customers, and I'll get into things like the environmental impact we've been able to achieve and our future plans to scale up. So to start with, who is CarbonCure? We're a technology company based in Nova Scotia, Canada, or Dartmouth, Nova Scotia, Canada, which is on the east coast of Canada. We've been around in one form or another since 2007. We started as a clean tech consulting company before shifting to technology providers about 5 years after that. It was founded by Robert Niven, who I met at McGill University in Montreal, where we were both studying how to make more sustainable concrete. And from there, we've grown into a company who has the vision to make this idea where you can introduce CO2 into concrete as a standard practice to make concrete production across the globe more sustainable. Our company mission is to reduce, if we can, 500 megatons of global CO2 emissions annually. And we have to do that by expanding our technology and generating new ideas for the industry to act more sustainably, and we can be a part of that. I will highlight that at this point, we are a venture-backed company. And so to get to this point, we have made the use of a lot of support from various parties. The one I will highlight in the middle, Breakthrough Energy Ventures, was our most recent investment about a year and a half ago. If you haven't heard of them, this is an investor group where they have assembled some of the world's top business leaders, and they're specifically looking to invest in clean tech companies. And they've identified 5 areas where clean technology can make the biggest impact in creating a more sustainable society. And buildings and civil infrastructure is one of them. So this is where part of the reason why we were selected as one of the, I think, first 8 companies they chose to invest in. And their ideas for what would make an investment is they had to see a technology, at least that had a pathway to having a 500 megaton per year impact. So this is why we state this as one of our goals. Just as a highlight of who these people are, you may not have heard of Breakthrough Energy Ventures yet, but you would probably recognize a number of the names on the list. The chair of the board is Bill Gates, but you can also find a number of some of the richest people in the world, Richard Branson, Jeff Bezos, Jack Ma, Mukesh Ambani, so a lot of these people have been very successful in business, and now they're turning their attention towards clean technology. Now I'm going to give a little bit of background on concrete. Why does society like to use concrete? It's a big part of our infrastructure, and in many cases, the reason will be because it's low cost. Concrete is something that you can make in your backyard if you wanted to. The materials are found in all environments, and they're relatively inexpensive. You're talking about a mixture of cement, which is a minor component, and your major components are sand and stone, which tend to be rather abundant. Concrete is also a resilient material. We see this again and again when the natural disasters, unfortunately, are affecting human developments, and they can find that concrete buildings perform very well in these types of situations. So when you have a resilient structure, it means that you're able to endure some of these undue influences, and now you can both extend the service life of the structure by continuing to use it. You can easily repair or recover from disasters. And so concrete has proven itself to be the right material for those applications. Furthermore, concrete is recyclable. Concrete at the end of its service life can be ground up, and it can be put into many different uses. And these uses may have different types of value that you may derive from them. One of the ones that's being developed nowadays is directly recycling the concrete back as aggregates for new concrete production. So if you can imagine that you have a concrete structure and you've been able to pulverize the concrete to an extent that you've got a graded material that you can use as a coarse aggregate or a fine aggregate in a concrete. This is a concept that's being practiced and investigated more and more. In contrast, steel is recyclable. Wood is not recyclable. If you have a end of service life wood structure, that wood ends up in the landfill and it actually starts emitting the CO2. So this idea that wood is keeping CO2 out of the atmosphere is more of a temporary position. Concrete is a versatile material. From the architecture and design community, they can have many ideas for creative expression, whether it be form or color or shape, or even where it's made. And concrete is able to respond to the challenges in many respects. And this is an example just of a highway rest stop in Norway. They had done an effort on the tourism board to develop new rest stops in Norway, and they said, let's make them architecturally interesting such that people would actually want to visit them. Kind of a strange thing, but they were very successful at it, and concrete played a big role in many of the rest stops that they made. So this is an example of one strikingly positioned and interesting to look at. Finally, concrete is a local material. If you look at the production of cement, the main ingredient of cement is limestone, and you can find limestone all around the world. Furthermore, if you're looking to take that cement, combine it with aggregates, you can find limestone all around the world. If you make a limestone aggregate, you can find other aggregates too. So if you wanted to make concrete, you should have no problem finding the material supply in your local area. And ultimately, we can consider concrete to actually be inherently a sustainable material. If you look at this analysis coming out of the UK, Chatham House report in 2018, where if you looked at the variety of materials that are used for construction, concrete shows up very favorably. For a unit mass of concrete, the CO2 footprint is the lowest amongst all the materials that they're looking at. And the embodied energy is also among the lowest. So if you're looking for a like-for-like replacement of concrete with another material, timber is going to have a greater energy and CO2 impact, and steel, plastic, and aluminum aren't even on this plot. They're orders of magnitude greater impacts than any of these materials. So we can highlight concrete with respect to other materials as being relatively a low carbon impact, low energy impact material. However, the discussion about concrete and sustainability often comes back to the CO2 emissions from cement production. So if you are looking at making concrete, one of your main ingredients of the binder system is going to be Portland cement. And the amount of cement that's produced every year means that we have a non-trivial amount of CO2 associated with the cement production. A carbon budget that's published every year pegs that at about 4%, and that's only the direct emissions from the cement production. So the calcination reaction, where you turn calcium carbonate into reactive cement, calcareous cement phases, releases the CO2 that's bound in the limestone. If you then further look at the cement production as taking energy required to heat up the limestone for calcination, you'll have another 40 to 60% emissions on top of what the calcination provides. So if you looked at the total emissions for cement production, the most accurate carbon budgets are coming in around 6 to 7% of CO2 emissions are associated with cement production and thereby concrete use. However, when we talk about that scale of CO2 emissions, if you go back a couple of slides, I told you concrete has a relatively low carbon footprint. Now, if we look at an example of the types of materials that are used for industrialized society, and this analysis was performed by a material scientist named Ashby a few years ago, and he presented this summary of the overall annual world production of materials on which society depends. And you can see we have fuels on the left in purple, then we have metals and alloys in orange, then we have plastics in blue, we have the more ceramic type building materials in gray, and we have wood and fiber materials in yellow. The thing about this plot, though, is that it's logarithmic. So you see a great difference in the amount of the materials that are produced, but it doesn't really drive home the scale differences. So if you took that data and refashioned it from the greatest scale to the least, you would see concrete, we're making about 25 gigatons of concrete around the world every year. Cement, we're making about 4 gigatons. Everything else is orders of magnitude less, being produced less than concrete. So we have this sustainability concern about concrete largely due to the scale of the concrete being used and produced. And this has increased about 50% over the last 10 years as the infrastructure needs of China primarily, but other emerging markets like India are turning to concrete to meet their highway, dams, building needs. So we can conclude that if we're going to talk about the environmental impact of concrete, we have to be conscious of this scale. Just because we're using so much concrete, we end up having this CO2 emissions, high CO2 emissions associated with that scale. The cement sector is, of course, not ignorant to this. They understand if they are going to meet the 2-degree scenario, or even now the 1.5-degree scenario, they're going to have to find ways to reduce the emissions coming from the cement and concrete sector. So in this example, this is the ideas put forward by the World Business Council for Sustainable Development Cement Sustainability Initiative. In 2018, they've since moved to a group called the GCCA, Global Cement and Concrete Association. But their roadmap has provided the framework for the thinking for the industry on how they can be more sustainable. And so if you look at the business as usual is the top of this plot. The dotted line represents continued improvement, but no specific action to be any better. And that's the emissions that will come from the calcination of limestone over the next, until 2050. They see certain levers to get the total amount of emissions down. The first 3 of them are well known. You can make a cement kiln more thermally efficient, which can make a small improvement. You can switch to lower carbon fuels. So instead of using coal, you can use something else that has a lower carbon footprint for your cement kilns, and that can make about a 12% reduction. And you can look at secondary cementitious materials, things like fly ash and slag, that will allow you to use less cement clinker in your concrete. That will have a bigger impact. But those 3 things together, which we already know how to do, we just are doing them more or doing them better, doesn't get us even, well, about halfway to, not even halfway, to where we need to be for the total reductions. So we say that the industry says we have to look at carbon capture, utilization, and storage, and or emerging technologies to help carry up the difference between where we think we can readily go with existing technologies to make up a bigger carbon reduction in the industry. And so we see ultimately, if you look at 2050, by far the majority of the emissions reductions will be associated with these technologies that haven't even been developed yet. Within those technologies, we have carbon capture and storage. So you just put the CO2 underground, carbon capture and utilization, which is the space we're working in, which is taking the CO2 and using it in another process. And then we have emerging and innovative technologies. So things that maybe aren't on the radar yet. We're developing new SCMs as an industry, for example. These will play a role too. CO2 utilization is the concept I'll be talking about in the rest of the talk as I get into specifically our technology. And what we're doing, what people do in this space is they take carbon dioxide and use it as a feedstock into some process. So for us, this is concrete production. And what happens is the CO2 is converted into the product. And so when you sell the product, there's some CO2 that is now, or carbon at least, bound in the product. What we are doing is what they would call the mineralization pathway. So if you had looked at this diagram on the right, to simplify it, we have a fuel. The fuel gives off energy, but it also gives off CO2 when you are combusting this fuel. Now you have the CO2, you can do 2 things to it. You can either turn it into a chemical, which is going to require additional energy to break this carbon-oxygen bond, or you can turn it into a mineral. So if you turn it into carbonate, this is a thermodynamically favored reaction. So that means it will release energy, it will be spontaneously, and it will also be permanent. So once the CO2 is locked in as the carbonate, it's effectively permanent. And that's where most of the carbon actually is in the world right now. It's locked in as carbonate minerals. What CCU looks to do is offer low-cost ways to convert this CO2, and the mineralization is a low-cost way. You don't have to add in new energy in order to convert the CO2 into a new product. So that means it can be done readily, simply, and with low energy requirements. So what specifically does CarbonCure do or offer? What we're doing is we're offering a retrofit technology to install at concrete plants. So we are offering, the truck is just branded. We don't offer the trucks, but we do offer the tank of CO2. We offer an injection system to deliver the CO2 and another box that we'll see that allows the CO2 to be injected into the concrete as the concrete is being mixed and batched. So it's just another ingredient in the concrete production process. Taken together, all of this is just a small modification. The producer is just adding this system as a retrofit. It can be done rather quickly, and they can get it up and running within one day. They don't have to change anything about where they're getting their cement or their aggregates. They don't have to change anything about the mixer or the way the concrete is shipped or even batched. The same equipment, the same materials, same supply chains, everything is the same except this small change. So it makes it easy for a producer to come on board. How this would work is best described as an analogy to a concrete admixture. So you could start in the concrete batch system. So when there is a new load of concrete being required, the batcher will say, for example, I need 8 cubic meters, 1 truckload of concrete, and it has this specific mix design. In this mix design, I need the certain admixtures. So then the batch controller communicates with the admixture supply, which is then dispensing admixtures into the concrete mixer. Either it's the mixer or the truck. Likewise, we can have a mix design that includes carbon dioxide. When that mix design is made, a signal is sent to the CO2 supply and the CO2 dosing unit to start putting in carbon dioxide into the mixing process. And so it's injected just like an admixture into the concrete as it's being produced. We take a supply of liquid CO2 from the industrial gas suppliers, and a tank of liquid CO2 is what is set up at the concrete batching plant. But when the concrete is injected, liquid CO2 is not stable at atmospheric temperature and pressure. So when the CO2 actually gets to the concrete, you actually have a mixture of solid CO2 flakes and gas. And so over the period of about 30 to 90 seconds during the mixing phase, we will have this CO2 being injected into the concrete. So this retrofit of the CO2 injection involves just putting this injection nozzle someplace where the concrete is being mixed. So it's either going to be a central mixer in what they would call the wet batch process, or the truck itself, if the truck serves as the mixer. What happens when the CO2 interacts with the concrete? Well, we can back up a little bit and say the concrete has started to mix. We have primarily, we'll just talk about the cement phase here, but we have water and cement in contact. The cement itself undergoes dissolution, and ions start entering the pore solution, and the very preliminary phases start to form. But if you want to boil it down, we have calcium going into solution. Once the carbon dioxide enters the system, the CO2 will form a carbonate ion in solution. Now, once the calcium and carbonate ions are both in the same solution, this is the most thermodynamically stable place for the calcium and carbonate to go. So we form calcium carbonate. That removes a little bit of calcium from the system, but ultimately, once this calcium carbonate has been formed, the rest of the hydration of cement can continue as normal. So you will form calcium silicate hydrate gel, calcium hydroxide, etringite, and so forth. So we have this. Essentially, conversion of CO2 is now converted into a solid material. We've done some looking around at the lab scale for evidence of this material, and we can find that upon injecting CO2 into a paste, you can see carbonate minerals, and they'll have a dimension of around 200 to 500 nanometers, it would seem. And so by taking this injection of CO2, you've now mineralized the CO2 in the concrete as calcium carbonate, and you've generated an in situ nanoscale calcium carbonate particle. And this particle acts as a nucleation site, and the downstream hydration processes that do occur will be impacted by this nanoscale addition. What we are seeing is concrete producers doing this can make stronger concrete. So this comes to our value proposition. If you have stronger concrete, it allows you to reformulate your mix. So if we walk through this presentation, the producer has made 3 batches of concrete, and they've measured the strength at 7 and 28 days, which are typical benchmarks for concrete strength. And so we have on the left is the control batch with their business as usual mix, no CO2. And then they have taken out 5% of the cement, and the strength has gone down, which makes a lot of sense since the strength of the concrete cement matrix comes from the cement that you put in. Then if you take that cement reduced batch and add CO2, you actually get a strength benefit that allows you to compensate for the strength loss you had. So you can see on the right, we went from 360 kilograms of cement in a cubic meter down to 342, which is about 18 kilograms of cement that was removed, 5%. And we can look at it in terms of the strength provided by the cement. So you only needed 7 kilograms of cement to provide an MPa of strength in the reduced CO2, reduced binder plus CO2 batch, and you needed 8 kilograms in the reference batch. So essentially, by adding the CO2, you've made the cement more efficient. You can provide more strength per unit of cement. That example was just a one-off with a couple of loads compared, but if we look at greater data sets, we can see that this strength production validates this idea that you can improve the compressive strength. So this is a producer who has been sending out a 35 MPa mix design, and where they made a cement reduction of 5.5%. And you can see there's no difference in the 28-day strength of the control in blue and the CO2 in orange. Since this is a 35 MPa mix design, the focus of the producer will actually be at the lowest end of the production. Statistically, you'll have a 95% chance of any batch being over 35 MPa. So if we even highlight the difference between where the CO2 batch ended up, we have probably evidence we can take out even more cement if the producer wanted to and didn't otherwise impact things like the way the concrete looked or finished. So the producer is very happy with this adjusted mix design. What that means for them is that when you take out the cement, if you look at the Portland Cement Association's environmental product declaration for the carbon impact of cement that is produced in the United States, they say cradle to gate, there's a 1.04 units of CO2 emitted for every unit of CO2 emitted for every unit of cement that's produced. So this producer, for each load of concrete, they end up saving or avoiding about 138 kilograms of CO2. And this is because the cement they didn't use has a CO2 impact. That also, for the producer, has monetary savings. So if you look at the price of cement coming in over $100 a ton, then you will have a savings each time that load goes out of about $18. And when you're talking to a business that operates as a commodity, and often the cheapest concrete wins the job, these type of savings can be a bottom line driver for the producer to act more sustainably. So the top line for us is that the concrete is more sustainable. The bottom line for the producer is they can save money in doing so. A more promising example of the same idea is a producer who has taken this higher performance mix design, designed to be about a 45 MPa mix design. They have a binder that's 50% cement, 37% slag, and 13% fly ash. So we would already say that this producer is doing a good job trying to make a sustainable mix. Their binder system has a 50% replacement of things that have a much lower carbon impact than does cement. But they said if we're going to add CO2 to this mix and get a strength improvement, we can use that to. And they actually went ahead and took out 20% of the cement, and they found that there was no difference in the strength. So for that producer, every time a load of concrete goes out, they were saving about 348 kilograms of CO2. And in generating value for their bottom line, they're coming in at about $57 of savings. You can't be sending this concrete out to a job if you're making it harder for the end user in any way. And so part of the things we have to be confident about is that the addition of CO2 is not doing anything to the fresh properties. And so this example from extended producer data where, oh, I see I've reported inches on the bottom, but it's an American producer who is coming in with concrete, and they measure the slump, which is a measure of the workability, and they're finding that there's really no statistical difference between the slump of the concrete produced with CO2 and the slump of the concrete produced without CO2. So they're confident that the concrete, when they ship to the job, will have the right workability. And further on the right-hand side, the fresh air content, which is important, particularly in environments where concrete will be freezing and thawing. We have examples here of the producers showing that the fresh air content of the concrete is not affected by the CO2. So we're not putting bubbles of CO2 into the concrete, we're putting mineralized CO2 into the concrete, so we're not affecting the air content in any way. These concepts tie into durability. If we're providing concrete into the broader market, we have to make sure that it both performs as necessary and it is sufficiently durable and lasting. So in our testing, we have established that not only to ourselves, but our producers have established through their own quality control data that we're not doing anything unacceptable by adding this CO2. Nothing unacceptable happens to the setting time. Nothing wrong happens to the workability or the slump. You can pump the concrete as you always did. The air content is where you need it to be. You haven't made the concrete warmer or colder. And the concrete can be adequately finished by the people who have to, work in the flat work type situations. Furthermore, once the concrete has been produced, the hardened properties, we have not collected any data or feedback that raises any concerns. This tiny amount of CO2 added to the concrete does nothing to the freeze thaw, does nothing to the concrete alkalinity or solution alkalinity. The density and color and texture of the concrete have not changed. So if we talk specifically about the durability tests, if you look at the testing, these are ASTM standards, C standards, with the exception of the RILEM, the B&Q tests. But these are industry accepted standards for testing concrete durability. And if we look at the results, in this particular case, you're doing a very small comparison of small data sets. So we didn't have necessarily the typical strength increases we see. This could be either just statistics or the dose wasn't quite optimum on this dose. But nonetheless, if we look at the rest of the durability data, we had maybe a small increase in flexural strength, no change to absorption, a small improvement in the abrasion, no change to the conclusions from the rapid chloride permeability test, no change to the resistivity of the concrete. The bulk chloride diffusion was not changed, no change to the freeze thaw. Shrinkage didn't change. Surface carbonation actually got a little bit better. Salt scaling didn't change, and the corrosion behavior was not changed. We've repeated this study a few times. So in a separate study, we saw very similar results. We had maybe a bit of a bump on the strength. Everything else was equivalent, maybe a bit lower. Not enough to say we're necessarily improving the concrete durability in any great measure, but this process does not make the concrete any less durable. Now, why would the addition of CO2 provide a compressive strength benefit? This is part of ongoing investigations for us. So we've looked at what happens if you take tricalcium silicate paste and then you mix it up and then you add some CO2. So we added a dose where we could observe products being formed, and then we freeze dry it to stop the hydration. And so what we're observing is that this CO2 creates this particulate calcium carbonate phase, even as early as you want to look at it. In our case, this was 40 seconds after the injection of CO2. So this is certainly, while the concrete is still being mixed at 40 seconds. What we're seeing, in addition to particulate calcium carbonate, is a fibrous gel phase. So this is impacting the chemistry to form additional calcium silicate hydrate more than with the control case at the same time. So if we just look at what that looks like under a microscope, this is the anhydrous tricalcium silicate. So before the water is added, this is the case where we've added CO2 and arrested the hydration at 1 minute. And you can find, if you were able to zoom in on these particulates, you would find these are where the CO2 has ended up in carbonates. And you do not see these small particulates in the unhydrated case or the default case. So after 5 minutes of hydration, we have a lot of activity in the system. So we have new gel has formed. We don't see the discrete particles anymore. They've been kind of buried by a lot of the new product that's formed. And if you compare that to something that had no CO2 in it, we can find maybe a reduced evidence of the reaction phase. So what's happening is the addition of CO2 is just kind of kicking off hydration, and somehow, some way, the phase assemblage is leading to a compressive strength benefit. Ultimately, a big question when you say CO2 plus concrete is, well, now you're carbonating the concrete. That's not a term we would use. We would say it's CO2 utilization for concrete production. Concrete carbonation refers to, in general terms in the industry, we're talking about service carbonation of concrete while it's in a building or infrastructure, and it's reacting and absorbing with carbon dioxide from the atmosphere. And so what that can do over time is consume the calcium hydroxide in the concrete and reduce the concrete pore solution pH. And if the pore solution pH goes down far enough, you can cause the ferrous reinforcement inside to start to corrode. And so this can be a durability issue. So we had to look at what is the CO2 doing to the pore solution pH. And so if we start on the right, nothing. The answer is nothing. So if you look at this addition of CO2 to the concrete, you've not done anything to the pH in service. And we have looked at this by taking concrete samples and taking out the pore solution and actually directly measuring it. And we do not see any difference. If we look at the earliest stages of hydration, so in the first few minutes, yes, you can add CO2 to cement, and yes, the CO2 goes down. You put carbonate ions into solution that can act as an acid. But that rebounds and you get no change within, or you're back to the regular pH of the system after about 10, 20, 30 minutes. So once the reaction has taken place and the secondary effects have equilibrated, you're back to the normal pH. So this reinforces the fact that nothing is happening to the pore solution alkalinity. Ultimately, the question is, is this approach sustainable? So if we run an environmental model, we can prove this. So we need to know the baseline CO2 emissions for conventional concrete production. We need to know what is the net impact of any mixed design changes we're having on any CO2 emissions, such as if you're taking out cement, you can save CO2. We have to know the CO2 that would be emitted during the capture and compression of the CO2, CO2 that's emitted during transportation of the CO2, emissions during the production of the gas injection equipment, emissions during the transportation of the gas equipment, and CO2 that's directly absorbed in the utilization step. Ultimately, then, we look at the avoided CO2 emissions from the avoided cement content. So as a case study, what this would look like in practice, there's a producer using our technology in Georgia, and they get their CO2 from a fertilizer plant. So if we say the energy input to get a ton of CO2 emits about 100 kilograms of CO2. And we can make that on the unit basis of the meter cube of concrete according to the dose we use. That concrete is then transported as a bulk load to an air gas facility in Cumming, Georgia, and then in what they call a less than load format to Thomas Concrete. And so we can look at the transport emissions for those two transportation modes, and we come up with about 28 kilograms of CO2 emitted per ton of liquid CO2 transported. And if you look at that on the unit basis, we're down to 5.5 grams of CO2 per meter cubed of concrete. If we talk about dosages, this producer is using about 0.11% by weight of cement dose. For their mixed designs, the amount of cement in the mix. Portland cement portion of the binder is 184 kilograms per meter cubed in this particular case study. So if you take that dosage rate by that cement loading, you'll come up with 193 grams of CO2 per cubic meter of concrete. And so if you looked at that amount of CO2, we're emitting about 45 grams of CO2 to do that. But if you look at typical chemical admixtures, and you look at their EPDs, you have about 1.8 kilograms of CO2 emitted per kilogram of admixture produced. And if you look at the National Ready Mix Concrete Association, they say producers are using about 3 ounces of a given admixture per cubic meter of concrete. So that means your admixtures come in with a CO2 footprint of about 160 grams of CO2. So our idea is that the 45 grams of CO2 to get the CO2 admixture in compares quite well with normal admixtures. So this is a small process emission, but it's not unusual. The equipment itself, you can talk about the emissions to create it, but then you say this equipment's going to operate over 20 years, and you talk about the amount of concrete that you're going to make over 20 years, then the emissions from the production and transport of the equipment are essentially very, very small per unit of concrete that's produced. Operationally, to run the equipment, say there's electrical energy, that will come up with CO2 emissions that's sensitive to the carbon impact of the electrical grid. With the direct CO2 absorption, this dose of concrete, we can model that about 93% of it is directly converted. So that's 179 grams. So if you look at an entire truckload of this producer ships about 8 yards of concrete each truckload. So it's about 1.1 kilograms total of CO2 that's injected. If you look at the material flows, this producer can take out 5% of the cement. That reduces the volume of the mix, so it's possible that they may increase the sand slightly. Not every producer does this, but it's possible that they will. If you did both of those things, because the sand is closer than the cement, you end up reducing the raw materials transportation emissions. And these steps on the transport avoid almost 300 grams of CO2 per cubic meter of concrete. Overall impacts, you can total these all up, the gas processing, the gas transport, the equipment production, equipment transport, equipment operation, and the CO2 that's not mineralized, all end up as being emissions at the project site. But we're also avoiding CO2 from the materials transport. We're directly mineralizing some CO2, and we're avoiding some CO2 emissions from the cement we don't use. So if you tie that all together, generically, they're looking at about 10 kilograms of benefit per meter cube of concrete. So to introduce these ideas to the marketplace, we have done it in a way that has been impactful. And it's important that we've come up with a brand new idea for the concrete industry that's both adoptable, meaning the market can accept and employ this idea, is profitable. The end users are incentivized to use this technology because it has a bottom line benefit for them to do so. And it's also scalable. We're working in ready-mix concrete, and this is one of the largest construction segments in the world. To talk about the adoptability of this technology, I can go back to what is installed at the concrete plant. It's a simple retrofit. There's nothing in what's being done here that is violating the standards of way concrete is being produced. None of this involves a capital expenditure, which means the producer can start being profitable with this technology from the very first month. An example here would be this producer with a baseline cement, and they take out about 17 kilograms of CO2. If one load is 8 meters, they're saving about 135 kilograms per load. So the monetary savings of the cement is almost $18. The CO2 itself comes with a cost. So you'll pay about $1 for the CO2 for each load, and you have a net CO2 benefit of 143 kilograms of CO2 per load of concrete. So the savings are actually 17 times as much as your CO2 costs. Your net value for each ton of CO2 that you actually utilize is over $6,000. And the net CO2 benefit is 56 times the amount of CO2 that you use. So if you use 1 ton of CO2, they are realizing 56 tons of CO2 benefit. In terms of scalability, we're talking about entering the ready-mix concrete market. Just in the US, there's over 5,500 ready-mix plants. They have an output of about 400 million cubic yards of concrete, and about 70% of the cement in the United States is used in ready-mix concrete. So if we can start reducing 5% of all the cement that's used in ready-mix, we can make a huge impact. Right now, the plot on the left shows our operations over the last 3 years and how much of the US market for concrete has actually been produced using our technology. We're approaching about 0.7% of all concrete produced in the United States is using this technology, and it's growing, as you can see. We can look at this technology as having been introduced in 2016, and we had a series of partners, and in the interim, we've continued to grow this network. We've started working with more and more partners. The partners that we know have installed in more and more plants. And if you looked at the total sum of technologies using our CO2 utilization approaches, there's 191 places around the world that are under contract right now. 120 locations are ready-mix plants, and to that 120 we have in the queue amongst the 191 are 47 more contracts that are just waiting to be installed. So in the very short term, that number of installations will grow. So for those 120 locations using our technology, you can see that as we've added producers, we've shipped more and more concrete. So in the orange bars is the amount of concrete that's produced each month over the last 3 years. The line shows the cumulative amount. So now we've exceeded 3.6 million cubic meters of concrete that has been shipped using our technology. This concrete is going into real projects. So just examples of them in Atlanta, you can go to San Francisco, the new LinkedIn campus. Ozinga, producer in Chicago, was involved in the flagship McDonald's sustainability project. They made the concrete. And in the bottom, a producer in Hawaii did a project for a Department of Transportation project. It was a highway on-ramp, and they actually had two morning news crews watching them finish concrete. This is a novelty piece of innovation in the industry that's attracting attention as the concrete is trying to act more sustainably. These ideas, the market is responding to them. So to specifically talk about two of those projects, this one used 330,000 meters of concrete and achieved a net benefit of 750 tons of CO2. So if you turn that into an amount of trees, 11,000 tree seedlings, if you planted them and grew them for 10 years, they would absorb 750 tons of CO2. So if you looked at that, that's about 37 acres of plantings of trees. Another project that was recently completed, the second largest single project using our concrete, was in Calgary, Alberta, and they had a de-icing pad made of concrete. So over the course of a couple of months last summer, they used 23,000 meters of concrete, and they realized this benefit of 160 tons of CO2 avoided. And we can say that when you talk about environmental impact, as we total up all the impact from all the concrete that's been produced, it's growing. Every load that goes out has about 100 kilograms of CO2 impact, and this is based on producer data. Total, we have exceeded 55,000 tons of CO2 emissions benefit, and most of that is due to avoided CO2. And the best way you can deal with CO2 emissions is not to emit them in the first place. So we're seeing that if you're not using this little bit of cement, that CO2 was never had to be emitted. A word about the sourcing of the CO2. For us, we source, or our customers, they source CO2 from the merchant market. So this is typically a high purity byproduct that an industrial gas supplier can economically capture and sell. Examples of that would be ethanol production, ammonia, or hydrogen production. They introduce the CO2 into the market. The price really depends on how much you're buying from them, but for us, typically $300 or $400 a ton. But that CO2 has no relationship with concrete production. So an ethanol plant has no relation to cement. So we know that a lot of CO2 is coming from cement plants. Could we start to use some of that CO2? It's not something that the merchant market is actually pursuing. The CO2 concentration of a cement plant flue gas is 15% or so. So it doesn't make economic sense right now for a merchant a CO2 supplier to choose a cement plant over an ethanol or ammonia plant. But long-term, there's logistics synergies. So the cement plants are producing cement for concrete production, so they can do so with minimal transport distances. So can we capture CO2 from a cement plant and give it to our producers at a lower cost? So if you look at around the world, cement plants are located basically near where infrastructure is produced. So that means they can minimize the transportation distances of cement to the concrete plants. And we say that if these concrete plants are going to use CO2, ideally we could take some CO2 off of cement. This idea is forward-looking, though. The idea that you can take all of the CO2 from a cement kiln and capture it is something that is thought to be 10 to 25 years away, depending on what type of implementation you want to do. But ultimately, this would serve to close the loop from emission to beneficial utilization in concrete production. So for us, producers using our technology are using about 50 kilograms of CO2 per day. So if you looked at the number of concrete producers a given plant would service, if they had a system that could capture 1 or 2 tons of CO2 per day, that would be enough for this technology. And that could possibly be done very economically in the sense that you do not have to integrate it into the entire plant. It could be just a slipstream capture technology. And we demonstrated this concept in Alabama 2 years ago. The industry is moving towards cement plant CO2 capture. The earliest efforts were done in Norway. The effort we did in Alabama in 2018 was tied into activities for the CarbonX Prize. But you've seen examples in China, Mexico, and coming online this year should be some projects in Italy, Austria, Canada, and the United States, where they're taking CO2 from the cement plant and they're developing capture technologies. And if we go back to the World Business Council for Sustainable Development and their cement sustainability initiative, they say that the carbon capture from cement plants is going to have to be a bigger contributor to the carbon reductions if the industry meets their environmental goals. And so they've said that's going to start ramping up in 2025. And even when you hit that, you're going to have to start capturing, dozens to hundreds and hundreds of megatons of CO2 from cement plants. If you're going to inject it into the ground, though, there's no economic case to do that yet. They're talking about putting carbon credits to do that, but if you're trying to run a business, it's not something that makes a lot of sense. So utilization is a way to take some much smaller, but some CO2 from that output and start putting it into an economically motivated use case. So that can be very scalable. You can put a small capture with any cement plant and take that CO2 and put it in the marketplace, either for customers using our technology or any other technologies in the built environment. Ultimately, we would say that if we can do this, we can talk about the circular economy for cement production. So you take limestone and you heat it up, you form your cement, but you're emitting CO2. The cement, in turn, makes concrete. The CO2 can be added back into the concrete and permanently bound. If we can actually achieve this, now we're recycling cement industry CO2 as a feedstock for concrete. And this is part of the long-term vision for the industry as a whole to be more sustainable. In conclusion, what we're doing here with this technology is we're impacting a conservative industry. We are working with innovative companies who want to try something new and cutting edge, but it's being proven to be easy to implement in this large market segment of ready mix. The retrofit makes it easy to do, and the fact that you're not switching your equipment means that this is a scalable technology. Furthermore, we know that if we're talking about CO2 utilization for the producer, if you just focus on the environmental benefits, the market adoption could be quite limited. So you have to come up with some other value to add for the producer. So for us, that is, if you're using less cement, you're able to save some money. So this motivates a producer to act more sustainably, but have a bottom line benefit. This bottom line benefit comes from improved cement efficiency. If you're adding the CO2 and mineralizing it in the cement paste, you can actually improve the compressive strength, and that allows you to reduce some cement, which is where your carbon benefit comes from. This ultimately demonstrates this carbon utilization pathway. So I'd hesitate to call this carbon sequestration, but it's carbon utilization to make more sustainable concrete. Thank you.
Great. Thanks a lot, Sean. I think that was fantastic presentation. I think we can open the session for questions. I would encourage professionals to unmute themselves and ask the question directly to Dr. Sean. Maybe I can start with my question, Dr. Sean. I think you mentioned about the mannerism of mixing CO2 and some kind of inefficiencies over there. In terms of overall percentage about how much carbon dioxide actually gets mixed with concrete vis-a-vis how much you inject. Are you looking at those, at improving those figures? I think you mentioned 45 out of 190 kgs being lost or something like that, right? So can you just sort of throw some light about how you're trying to manage reducing those figures, or you believe that you can't make the process more efficient than what it currently is?
Yeah, good question. When you do inject some of the CO2, you not all of it does convert, particularly if you talk about putting gas into something, while the CO2 is heavier than air, there might not be the same driving force for it to react with the concrete as a solid CO2 flake, which can stick to the mixing concrete and be readily mixed in. So I don't think there's much we can do to make that all better unless you went to full solid CO2 injection, which is a lot more expensive. So you took the gas out. But we focus on the fact that this small amount of CO2, even if none of it got absorbed, as a thought experiment, if none of it got absorbed and you still got a strength benefit, as long as you're taking out cement, you do not have to take out very much cement at all to cancel out the dose or any CO2 emissions that were realized. So when you see producers having a 50x multiplier, 1 ton of CO2 goes in, unlocks 50 tons of benefit. That means, very small cement reductions can make this a net carbon positive technique.
Yeah, right. And the other question actually I have is, you mentioned about cement producers being a supplier of carbon dioxide as well. I mean, in fact, if you're looking at a 20% reduction of cement once you start blending carbon dioxide, would that actually not discourage cement producers to be onboarded with this whole idea about capturing carbon dioxide, and because ultimately it's going to reduce their business to some extent or hamper their business?
True. I think that way of thinking is more traditional business as usual thinking. When we look forward, the industry knows it has to be more sustainable. From a cement producer, if you want to apply conservative thinking to it, you can say it's very expensive to make a new cement plant. So we know concrete demand is projected to increase even further. Does that mean we have to build more cement plants? Well, now you need a quarry. Now you need a bunch of people who don't want a quarry in their backyard. And wouldn't it be just easier to use the cement plants you already had? So that's an idea where you might use less cement, but if we don't have to build a new kiln, for example, it can be an easier way to get more out of your existing infrastructure.
Yeah, sure. Do we have any other questions coming from anybody else over here? Feel free to unmute yourself and ask the question directly.
Hello, yes, it's Andrew Dunster from BRE in the UK. I just wondered if Sean could tell me if there's any practice in application of this technology in the UK at all on real full-scale projects.
Yeah, I showed you a map of the producers we were working with, and you may have noticed it was a map of North America, with the exception of a small inset of, oops, I'm going to go to that slide. A small inset of the producers that we have in Singapore. I can't remember where that slide was. The point is, no, we don't have any producers in the UK right now. We are in discussions with European partners. So we do expect to be operating in the United Kingdom, if not this year, then next year.
Okay, great, thank you.
Here it is.
Do we have more questions? Anybody else would like to ask a question over here?
Yes, if I could ask a question, please. Thank you. That was a very interesting presentation. It was really actually, has this material been used at all, maybe on sort of airfield pavements or anything like that, or is it all just traditional concrete use? Sort of what is the what is this material primarily being used for in the trials and that you've put together?
Most of the producers are sending this concrete to just regular civil engineering jobs, buildings, sidewalks, building foundations, housing. We do have examples of people who have been looking at precast, so that will get into, you know, pipes or large elements, bridge segments. And we do have the example I showed of the project in Calgary, where they had the de-icing pad. So this is the best example of someone who's used concrete in a paving application. So it's really up to the producer. You know, they will use our technology and validate the value it provides to them, and then they will see what projects can they use it on.
Yeah, Dr. Sean, a question from me. How do you see application of carbon dioxide impregnated concrete for offshore projects or marine projects or projects where we have, you know, water treatment plants or sewage treatment plants or similar other places where concrete is directly in contact with water or slightly corrosive environment of water, basically? So is that something that you have a track record for, any projects that you can actually think about where you have actually used this for similar applications?
I'm not sure I can think of specific projects that I'm aware of, but while we were developing this technology, we were testing the durability. And that's one thing that we did. We did what would in Canada be called a C1 or a C2 mix. These are mixes for high durability environments, such as, you know, offshore. And we made concrete using that mix design, using the CO2, and we've actually put it in a test facility in Maine, where it's getting freezing, thawing, wetting and drying, and the action of the ocean. So this concrete has been sitting there for 3 or 4 years, and it's periodically monitored. So while we may not have a project specifically yet, this is something we can point to, and ultimately there would be some validation if you were trying to do something like that in standard tests to be done.
Right, there's a question from AH. AH, are you not able to unmute yourself? You can directly unmute and ask the question yourself. No mic. Okay, fine. So his question is this application compatible with air entrainment? Is there a limitation on concrete grades?
Yes, we didn't have it in the presentation, but one of the first things we looked at in terms of that question was the air void system. And so we found that the CO2 would go in, and you've not changed the void spacing, you've not changed the size of the bubbles. And that was published in a paper, I'll pull up the slide, in 2016. So this paper, if you look at hardened air void, the bottom line, that was where we tried to directly assess the air treatment. In terms of concrete grades, I think the biggest issue we are facing is that the idea that certain end users of concrete are prescriptive, and they say that the concrete you will give me will have this amount of cement in it, for example. And so if we offer something to the producer and they're giving this concrete to the customer and they're already using the minimum amount of cement, they may choose not to use our technology on that mix design, because if they can't use the technology to produce the cement, they may not need the technology to provide extra strength. So in that regard, that's more of a case-by-case situation rather than a concrete grade situation, but good question.
Yeah. Do we have any other questions? Maybe in the interim, I can ask one. Dr. Sean, what is the anticipated performance of the concrete in seismic scenarios? And what is the longest surviving building where carbon dioxide impregnated concrete has been used so far?
For the seismic question, I think that would come back to the performance of the concrete as a material. So if you're seeing that the compressive strength and flexural strength is acceptable, then that's what you would input into your seismic modeling. So since ultimately we're not changing the concrete much at all, if you're not taking out cement, you can get a strength benefit. If you are taking out cement, this concrete performance is unchanged. So seismically, it should behave the same as the existing baseline concrete would have performed. In terms of the longest projects that are existing, we can go back to a project in Halifax, Nova Scotia, where we developed the technology, and that would go back to, I think, about 2015. So at that period would have been the earliest concrete produced commercially for this technology.
2005, is it?
15.
15.
So
okay. Yeah, thanks.
5 years.
Sure, no problem. Do we have any other questions? Otherwise, we can close the session for today. Just let's give 10 seconds for people to respond in case they have any more questions. Okay, there's one question over here from Manga Bhai. If you use triple blend systems, what are the properties? How do the new range of PCE performance?
Okay, two questions there. I guess, does this work in blended cement systems? This example was an example thereof. It had both slag and fly ash. Across our 120 producers, we've had them use this concrete on all sorts of mix designs. So we've seen just about everything these producers will put in a cement mix, whether it's type F fly ash, type C fly ash, slag, limestone additions, silica fume. So they haven't reported any unusual interactions between the CO2 and these systems, neither in the fresh state nor the hardened state. In terms of the interaction with admixtures, again, we're depending on the producers to identify anything that might be unusual. We haven't seen them talk about anything that's concerning them. We've had examples of synergy between CO2 and a non-chloride accelerator. So this would allow a producer to get the accelerating effect they want, but use less of what could be a very expensive non-chloride accelerating admixture. So that's an example. So there may be things that we will yet discover.
Right. I think probably we are already exceeded our time by 15 minutes. So I would really like to thank Dr. Sean over here to have given us a fantastic presentation. So thanks a lot, Dr. Sean. For those who were not able to join us through this presentation, we will be probably sharing the recorded link to our professionals who had registered for this event and could not make it. So thanks a lot, Dr. Sean, and thanks everybody to join in. Have a great evening and have a great weekend. Thanks a lot. Bye-bye.
Thank you very much. I realize I went a bit over time. I apologize.
That's perfectly fine. No problem. Thanks a lot. Bye-bye.
Thank you.